Welcome to the U.S.-Israel Energy Center second annual event. My name is Eitan Yudilevich, and I'm the Executive Director of the Bird Foundation. We are very pleased that you are joining us today from the East to the West Coast in the U.S., from Israel, and from other places in the world. Before we start, let me point out that this webinar is being recorded. The recording will be posted on the U.S.-Israel Energy Center website. If you have questions or remarks, please share those with us using the Q&A tab. We will do our best to respond following the webinar. The U.S.-Israel Energy Center was officially launched in 2018 after the signing of an implementation agreement between the U.S. Department of Energy and the Israel Ministry of Energy. The first call for proposals was published in April 2019, and the second call for proposals was published in July 2020. The consortia presenting today were selected in a very competitive process by the stakeholders of the program, the U.S. Department of Energy and the Israeli Ministry of Energy, jointly with the Israel Innovation Authority. We have a busy schedule ahead of us with the goal of giving our audience a snapshot of the very broad research and development activities carried out by the four consortia of the Energy Center in the topics of energy storage, fossil energy, energy cyber, and energy water nexus. In this event, you will see and hear summaries of their activities, which were initiated in August-September 2020, except for the Energy Cyber Consortium, which was launched in November 2021. The consortia are a varied combination of US and Israeli universities, companies, research institutions, and utilities. In the US, there are 25 participants located in 14 different states. In Israel, all the major universities are either consortium leaders or members, and 11 Israeli companies are consortium members. Despite the travel limitations imposed by the pandemic, we see significant cross-border collaboration between the US and the Israeli entities, which is a major goal of the program. We expect to see even more of those collaborations being developed as the work progresses and the interactions increase. We're going to hear opening greetings from Mr. Dror Bin, the CEO of the Israel Innovation Authority, and from Dr. Gideon Friedman, Chief Scientist of the Israel Ministry of Energy. Then, Ms. Julie Cerqueira, Principal Deputy Assistant Secretary at the Office of International Affairs, U.S. Department of Energy, will provide the U.S. DOE point of view in her keynote address. Most of the time will be, of course, dedicated to the overview and updates delivered by the four Energy Center consortia. A couple of words about the Bird Foundation. The Bird Foundation's mission is to promote and support collaboration in R&D and innovation between US and Israeli entities. Many Bird Foundation sponsored projects have led to breakthrough products with more than $10 billion in sales. In 2018, the stakeholders selected the Bird Foundation to operate and manage the U.S.-Israel Energy Center, expanding significantly the scope and character of the work done by the Foundation with the approval of Bird's Board of Governors given in Resolution 391, dated October 2, 2018. And again, thanks for joining us. And now, I'd like to introduce Mr. Dror Bin, CEO of the Israel Innovation Authority. Dror, please.
Thank you very much, Eitan. Hello, everyone. I'm very happy to be here. I believe that one of the main advancements of the past year is that no one has to present the climate change challenge and elaborate on its ramifications. I think that we all apprehend the critical situation we live in and that we need to act. We all also understand that one of the main leverages humanity has in mitigating and adapting to climate change is technological innovation. Unfortunately, many of those innovative solutions were not even invented yet. In the Israel Innovation Authority, we believe that the Israeli innovation ecosystem can greatly contribute to this global need. In a recent report we issued, we mapped the vibrant climate tech ecosystem in the country. Around 650 active startups. Every year, 10% of the newly established startups in the country are climate-related, relevant and strong academic research, lots of investors' interest and more. These days, we are promoting, together with our partners in the government, such as Dr. Friedman, that will speak after me, and in the industry, a national program for climate tech, followed by a robust work plan which will stimulate the ecosystem, provide governmental support, elevate barriers, and provide the backwind needed for the climate tech ecosystem to rapidly evolve. In this regards, I'm very happy to see that our both nations are leveraging the well-established collaboration platform of the Bird Foundation to tackle climate and the energy challenge via the Energy Center initiative, supporting deep collaboration between industry and academia on both sides. By creating these 4 early-stage R&D consortia, we are promoting industry and academic collaboration on both sides. We increase the pool of knowledge, involve industrial leading players, help commercialize early-stage technologies, and enable greater impact. Tackling the most significant challenges of the energy sector, like alternative fuels, energy storage, energy cybersecurity, and the energy-water nexus, will not only help us to reduce the emissions, but will also secure energy sources and the economic development of both nations. I would like to wish lots of success to the 4 consortia, and I'm looking forward to seeing the advancements they will make. And I hope that this collaboration will be a model for further collaboration between the countries on these climate issues. Thank you very much.
Thanks, Dror, for your leadership and support. Next, allow me to introduce Dr. Gideon Friedman, Chief Scientist at the Israel Ministry of Energy. Gideon, please.
Hi, good evening and good morning, everyone. I'm really honored to be here. I just thought about this meeting before we started, and I say to myself, here we meet with the background of tens of scientists, great scientists with amazing minds and ideas, and I'm really impressed about this project, which is a joint project between the US and Israel, which we have been able to set up and start about 3 years ago. But the work before that was quite intensive and very important. And many people don't realize that in order to bring innovation, there is a lot of work in the background to allow that and to think about it a lot. We can see the crisis now, for example, between Russia and Ukraine. We see our climate crisis. These crises show us very clearly how technological solutions could solve the problems, but they are still not here. The solutions are still not here. We would like to have better solutions. We would like to stop our dependence on fossil fuels and on gas from Russia, for example. We would like to be able to use clean energy 100%. All of these wishes we need to make a reality, and this can be done mostly by technology. So I think when I'm thinking about this huge collaboration, the Energy Center of Excellence between the US and Israel, I'm really hoping that the forethought of the people who invested in planning and preparing this Energy Center will actually bring excellent results that will take us closer to the goals that we want with respect to the climate problems and also the other energy crises that we may face. So I'm very interested to listen to the speakers today and the progress that they made during the last year. And I wish everybody a joyful evening and presentations. Thank you.
Thanks, Gideon. Thanks for your leadership in promoting R&D collaboration between the US and Israel in energy for many years. Now, it is my honor to introduce Ms. Julie Cerqueira, Principal Deputy Assistant Secretary, Office of International Affairs at the US Department of Energy. Ms. Cerqueira, please, the stage is yours.
Thank you, Eitan, for the kind introduction. I'm pleased to be speaking with you today with Mr. Ben as well as with Dr. Friedman. The U.S.-Israel Energy Center is one of the best examples of DOE's collaboration with international partners in applied research and development. The 4 topic areas, energy storage, energy water nexus, fossil energy, and cybersecurity for energy infrastructure, address some of the most important areas of DOE's research. Addressing them as part of the U.S.-Israel Energy Center allows us access to the tremendously innovative work of our Israeli partners. In cybersecurity for energy infrastructure, as just one example, Israel has a depth of expertise and experience dealing with real-world threats and a wealth of companies and institutions that are rising to that challenge. The United States, for our part, brings the depth of knowledge from DOE's national labs as well as from our technology sector. And similarly, both Israel and a number of US states face acute challenges in the energy-water nexus as energy-intensive desalination becomes ever more important in states including California as well as in Israel. Combining our efforts at meeting these challenges benefits both the United States and Israel. Beyond the clear benefits of advances in critical technologies, the Energy Center demonstrates the importance of both governments' place on innovation that drives the energy transition. We're also working together on shorter-term projects, focusing on green innovation under the annual Bird Energy Joint Grant Program. To date, Bird Energy has funded 60 cooperative Israeli and U.S. clean energy projects for a total government investment of $47.5 million. And that has helped to leverage $62 million in funds that are matched by the private sector to commercialize clean energy technologies. What a huge success. It's our hope that the technologies our collaborations help bring to market will benefit not just the United States and Israel, but the wider region and the world. Grant programs like the Energy Center are just one part of our joint commitment to the energy transition. Israeli scientists visit the national labs every year to work on a variety of projects together. Our cybersecurity divisions maintain close relationships, as do our offices that handle energy efficiency, renewable energy, and reducing methane emissions from natural gas production. All of this cooperation is supporting our broader shared energy transition goals. And I think, as Dr. Friedman has just so wisely spoken, it is so critical, especially now, for us to move away from fossil fuels, especially when it comes to maligned actors, because it's leaving us vulnerable and allowing them to weaponize energy. So the clean energy transition could not come faster. We at DOE have big plans for energy innovation that we call Earthshots. The first Energy Earthshot, which was announced in June of last year, sets an ambitious yet achievable cost target to accelerate innovation and spur the demand of clean hydrogen by reducing the cost by 80%. The second Energy Earthshot, the Long Duration Storage Shot, aims to achieve affordable grid storage for clean power, anytime, anywhere, by reducing the cost of grid-scale energy storage by 90% for systems that deliver 10 or more hours of duration within just this decade. And our third Energy Earthshot, called the Carbon Negative Shot, is the all-hands-on-deck call for innovation in technologies and approaches that will actually remove CO2 from the atmosphere and durably store it at a meaningful scale for less than $100 per net metric ton of CO2 equivalent. Those are really big goals, but we know that we've got to reduce the cost of these technologies to make sure that they are affordable for everyone. We expect that we're going to announce even more energy shots over the coming year, so stay tuned for more. Each of these goals is going to require collaboration with our partners, especially with Israel, and each of them starts with basic and applied research. The success will be the culmination of many individual projects that build on each other to achieve our goals. The U.S.-Israel Energy Center managed projects all help in some way to further these or future Energy Earthshots, and I'm proud to represent DOE here, bringing attention to their important work. I want to recognize the Bird Foundation for its critical role in the success of the Energy Center. Thank you so much. Eitan and his team have just served as outstanding stewards of the program, and I especially appreciate the 4 consortia that are pushing forward with U.S.-Israel Energy Center projects. COVID has presented a unique and unexpected challenge for both the management of the program and the consortia doing the work. I'm delighted with the progress that has been made despite these obstacles. I hope some of you will be future participants in joint US-Israeli efforts, especially around these energy innovation programs. And again, I'm just so thankful for the opportunity to join this esteemed panel and also to speak with this audience. Eitan, over back to you.
Thanks very much, Mr. Kera. Great. We thank you very much for those insights. Actually, we're very proud of our collaboration and long-term relationship with DOE, hoping to do much more, and also hoping to meet you in person pretty soon. Thank you. Great. So we are now ready for the presentations of the 4 consortia. For the presentation of the Energy Storage Consortium, I invite Professor Paul Albertus, University of Maryland, and Professor Malachi Noked, Bar-Ilan University, the consortium leaders. Will join them Professor Sang-Bok Lee from the University of Maryland to present one of the ongoing projects. Gentlemen, the stage is yours.
Thank you, Eitan, for the kind introduction. And on behalf of our entire consortium, we thank the sponsors for their support and the Byrd Foundation for their management of this program. We also like to thank the consortium participants, many of whom are here today, and in particular, Sivan Okashi-Pollock and Kathy Stevens for their assistance with this program. As Eitan mentioned, I'm Paul Albertus. I'm the co-PI for the Energy Storage Consortium of the Byrd Energy Center. I'm also assistant professor at the University of Maryland and the associate director of the Maryland Energy Innovation Institute. I'll now ask each of my co-presenters to briefly introduce themselves.
Hello, my name is Malachi Noked. I'm an associate professor at Bar-Ilan University, and I'm the leader of the Israeli side of this important consortium. I'm very happy to be here today with this very exciting event.
Hi, I'm Sang-Bok Lee, a professor of chemistry and the director of Maryland Nano Center here. And I'm pleased to meet all of you, and we're proud to present our work today.
Great, thank you. And as you can see from our title slide, we have a slide that we can share. There we go. We've given ourselves a name, UISEC, for the US-Israel Solid Energy Center. And today we'll share both a brief overview of our consortium as well as an example of one of our current international collaborations. So as one of our speakers already mentioned, we've all been working on how to work together during the last couple of years, especially with COVID, but also just our international collaboration. On the left here, you'll see one of our many Zoom gatherings, the team of people that are involved. We've also recently experimented with meeting in the metaverse. This is an example of a poster session, a virtual poster session we held, which had very good feedback. So we're finding ways to work together and new ways of working together within our consortium, and we look forward to meeting together in person for the first time in June. So our energy storage consortium is focused on batteries. Batteries are enabling for numerous applications. You can see a table there on the left with some of the many areas where batteries are used, and a bit more detail with some examples on the right-hand side that you can see here, including applications like defense, transportation, aerospace, and grid. So energy storage is really important for a number of different application spaces. Obviously, there's been some big shifts in the energy storage industry recently, primarily driven by lithium-ion battery technology. This is a market that's going to undergo approximately tenfold growth in the coming decade and eventually achieve a market size of hundreds of billions of dollars per year. This is principally being driven by the expansion of passenger electric vehicles. And despite this rapid growth, there's still a range of important gaps in a few different areas. Those include the energy density of batteries. That's basically how much energy per mass or volume. The safety of batteries at the cell or material level, we'll say, and also their costs, which is especially important for EVs and grids. And even as people work to improve battery technology for passenger vehicles, improvements could also enable entirely new types of applications in long-haul trucking or other functions in aerospace, defense, or medical. And so our consortium is focused primarily on both battery cell technology, but also enabling tools and components of batteries for high value markets like space and defense. And then we may later transfer some of those technologies to higher volume markets. One other aspect of our consortium, even by 2020, more than 70% of annual lithium production was used for lithium-ion batteries. And so if you look at this figure, you can see how much expansion will be required in the coming decade. Sodium salts are both more widely distributed and abundant, as well as less expensive than lithium salts. So we're also pursuing sodium-based solid-state batteries. So the schematic here in the upper left shows the kind of key components of a current lithium-ion battery. And our basic goal of our consortium is to replace the liquid electrolyte that's present with a solid electrolyte, which in turn will also help us replace the graphite electrode that's shown on the top with a metal, either a sodium metal or a lithium metal anode material, and that will allow us to significantly reduce the size and therefore increase the energy content. And one other key advantage of this is that the liquid electrolytes in lithium-ion cells can burn if they're exposed to oxygen, but many of the solid electrolytes, for example, LZO is one composition, is actually already an oxide and therefore stable in a flame. So again, our goal or our approach here for accomplishing these three objectives with solid-state electrolytes is to enable the use of lithium or sodium metals to increase energy density, use solid electrolytes to improve safety, and to reduce the amount of mass or volume per energy stored to help reduce cost. Our team is composed of a number of leading universities and companies working in this area. There's two universities in Israel, Bar-Ilan and Tel Aviv universities, working on battery chemistries, coating, cell technology, interfaces. There's a startup company, 3DB, focused on battery cell development, and also a spin-out from BIU focused on materials informatics. On the US side, we have a number of groups at the University of Maryland focused on thin film batteries, coatings, modeling work, solid electrolyte development, et cetera. A company in Colorado called Forge Nano focused on industrial scale atomic layer deposition, which we'll hear more about. A spin-out from the University of Maryland focused on commercializing lithium metal solid state batteries called Ion Storage Systems. And finally, SAF, which is currently one of the leading battery manufacturers for defense and aerospace. And with that, I'd like to turn over the presentation to the Israeli PI, Malachy Noked.
Thank you, Paul. I will continue as Paul presented our partners and also the main goals of our consortium. This is a slide showing how our consortium is structured, split it into 4 tasks. So we really start from the basic foundation, the building blocks of the batteries, including synthesis of solid electrolyte and cathode material on task number 2, interfacial engineering of this material in task 1, modeling and informatic studies of the electrochemical behavior of these materials in task 3. And we are very commercial-oriented consortium because all the material we make will then be on task number 4, tested in a full cell development. Next. So some of the fruits already came out from our consortium. We are very proud with our joint publication of Bar-Ilan University and University of Maryland. You will hear more about it in the second part of our talk. We have also works published on the modeling by the group of Professor Albertus and work on the anode-free battery from the group of Professor Peled. With that, I would like Professor Sandbach-Lee to present the second part. Thank you.
Okay. As Malachy Noked introduced those significant achievements that our center made. Among those significant achievements, I'd like to highlight the exemplary, collaborative, and synergistic efforts, which is development of advanced thin film deposition processes on active cathode material. Next slide. As you know, the battery is composed of electrodes and electrolyte. And interfacial engineering and engineering interfacial resistance is one of the most important problems in battery science and development research. In order to overcome these interfacial resistance, our approach is to use stable ion conductive coatings. Next slide. And I like to emphasize, this slide actually shows that a collaborative workflow, and I really like to emphasize that all three institutions, including UMD, Bar-Ilan University, and Forge Nano, our expertise is highly complementary. And as you're seeing here, the UMD team, especially Gary Rublev group, is a pioneer of atomic layer deposition science and engineering for battery materials and their interfacial control. And in the next, the Bar-Ilan University team is implementing those atomic layer deposition processes that UMD developed and adjust and modify to coat powder particles of a battery material. Then later, to scale up the powder coating processes to a production scales in the Forge Nano. Next slide. This is a good example. The UMD team developed a atomic layer deposition process for lithium phosphorus oxynitride thin film materials that can be used as a lithium ion conducting material, and at the same time can be used to control those interfacial resistance between electrode material and electrolyte. And in addition to that, the good news is that the UMD team has already achieved the development of a process for sodium phosphorus and oxynitride thin films. And in the next couple of slides, and you will also hear that how the Bar-Ilan University implemented this fundamental science and interfacial engineering to coat a powder particles for a industry standard cathode materials. The next slide, I will pass it to the Professor Noked here.
Thank you, Sandbok. So what you see here is the inside of our reactor for powder coating. And Paul, if you can click, there will be a play of the, so no, click back on the cartoon, yes. So you can see there is a tumbler over there that is rotating, and the reactor is actually closed under operation. Now you see it open. Inside the tumbler, we are putting powders of active material, and we are capable of adjusting the process developed at University of Maryland. So we take process of LiPon, for example, which is lithium ion conductive thin film developed at Maryland, and we adapt it to powder coating. What you see on the side, on the right hand, is the transmission electron microscope image of a coated cathode surface, 3 nanometer thin. So you take 1 meter divided by milliard, 3 units of that, lithium ion conductive thin film on cathode material. Additionally, as Sandbok mentioned, University of Maryland were already developed a NAPON, so the sister sodium ion conductive, and click, Paul. And we already took this process developed by the group of Professor Rublev and Sandbok Lee, and we are capable of now coating it on surface of active material for sodium ion batteries. Next slide. Thank you. What you see here is a cycling performances of battery. And if you look on the red one, which is higher in values, this is the protected cathode. The cycle number at the bottom just indicates how many times we cycled our battery. And as it is observed, the coating significantly improved both the amount of charge we can put of our battery, but also the longevity of the battery, maintaining better capacity, therefore higher energy with time over cycling. This is using the LiPo process developed at University of Maryland and applying it on a cathode powder at Bar-Ilan University. Next slide. Additionally, we were also able to manipulate the process of the phosphate that was developed at University of Maryland, adding into it some zirconium, putting it an active material, and what you see on the right hand is a special capability of transmission electron microscopy that it was done at University of Maryland in order to analyze the coating of a powder that we did here at Bar-Ilan University. And the battery studies of these cathode are presented in the next slide. More details you can find at our joint publication that the reference is on the bottom of this slide. Again, as you can see, let's look on the green. The coated powder with the lithium zirconium phosphate significantly improved the capacity, meaning the energy density of the battery, and also the long-term stability, the longevity of this battery. And the cathode material used is really commercially oriented. This is the holy grail of cathode material because it's low cobalt, high nickel. It's aiming to have low cobalt contained cathode material due to the price and due to the enhanced capacity. So this is already published as a joint publication, and we are very proud with this success. We are aiming to do so also with the sodium systems and with the solid state batteries. With that, on behalf of our consortium, I would like to thank you for listening, and I hope you enjoyed our work.
Thank you, Professor Albertus, Professor Noked, and Professor Bock-Lee. Great work and great collaboration, and I think you gave a great example of how a consortium works across border between the US and Israel, including the company, which is exactly what we're trying to achieve in the US-Israel Energy Center. Thank you very much.
Thank you.
Thank you.
So, for the presentation of the Fossil Energy Consortium, I invite Professor Dan Shantz from Tulane University and Professor Simon Emanuel from the Hebrew University of Jerusalem, the consortium leaders. Will join them Dr. Brian Sama from Tulane University to present one of the ongoing projects. So the stage is yours, Dan and Simon.
My name is Dan Shantz. I'm a faculty member at Tulane University. And I have Professor Simon Emanuel here with me. And we're going to talk to you today about some of our work in the Fossil Energy Center. And Simon and I will give an overview, followed by Brian will give a nice update on a joint project between Tulane University and Haifa. I'm assuming everybody can see the screen. So we're the GOMET Consortium. This is the Center for Fossil Energy.
We cannot see the screen.
Okay, good. Oh, we'll fix that. There we go. I apologize about that. Apologies. There we go. There we go. All right. So
now, yes.
Again, apologies on that. So the goal of GOMET, or the Fossil Energy Consortium, is we want to create and deliver technologies that reduce carbon emissions and improve environmental safety in the global energy sector. We're all aware of the need and use of fossil fuels at the moment. One of the main focal points of our center is we would like to use these fossil fuels and extract them in the most efficient, safe way while identifying ways to mitigate their impact. The world as it is today, we have approximately 80% of global energy is fossil fuel based. So we would like to utilize these resources in a way where we minimize environmental risk and we maximize their utilization. So one of the solutions that we can talk about is doing what we can to drive towards low carbon energy production. And one way we can do that is to utilize the resources we have as efficiently and as safely as possible.
Sorry, Dan, we see your first slide. Please move to slideshow.
Yes.
I'm in slideshow.
Yes, please.
Okay, so on my side, I appear to be in slideshow.
So stop share and share again, please.
Apologies.
Yeah, you might need to share your whole screen for it to work.
I'm terribly sorry about this, everybody.
No problem. Share the screen and fine.
Are we
Okay.
there?
Now we're good.
I'm terribly sorry, y'all.
Don't worry. Go
So
ahead.
if we're talking about the scale of going back to this, of not using these resources properly, what's the cost of that environmental safety? Unfortunately, being in the Gulf Coast, we have firsthand experience with this. If we look at the Deepwater Horizon disaster in 2010, in the end, this is likely to cost close to $65 billion. So there are clearly huge incentives to doing this in the most efficient, safest, most responsible way possible. So to that end, the partners in the consortium, there are 10 organizations between the United States and Israel. In the United States, Tulane is the lead organization. We have Argonne National Lab, LSU and the University of Louisiana as the US partners. Hebrew University at Jerusalem is taking the lead on the Israeli side. And we have colleagues participating from Tel Aviv University, Haifa, Technion, NewMed Energy, and the Geological Survey of Israel. So it is a diverse team. We have numerous programs working across the Atlantic, so to speak, and as some examples of that, we can talk about, we have 6 projects developing tools crucial for geological carbon storage. We have 2 projects looking at methods for carbon utilization. I'll talk about those at the end. And we have 5 projects aimed at mitigating environmental impact of gas production. And over half of these have joint collaborations between the US and Israel. And Professor Summa will do a nice job giving you an overview of one of those in a minute. So that's the overview. And from here, I'm going to hand it off to Professor Emanuel to walk us through the themes.
Okay, great. Thanks very much, Dan, for that introduction. So our strategy for tackling this problem was basically, we split it into 4 different themes. In the first theme, which is basically developing tools for carbon storage and gas reservoirs, was focused on developing tools that could really be of dual use. So it's not just tools that can actually be applied to extracting gas, but also to injecting carbon dioxide into the subsurface. So one of the main problems, one of the main challenges to this is characterizing the subsurface. And by that, Dan, could you pass to the next? Okay, so in order to do that, either inject carbon dioxide or extract gas, we really need to develop reservoir models. And those incorporate huge amounts of data across scales, so we can have pore scale models that look at what's going on within pores at the nanometer and micrometer scale. And we're trying to incorporate that kind of data into something that's called a lithofacies model, which tells us how rocks change both laterally and vertically. And this involves huge amounts of data and analyzing huge amounts of data. And that presents a really quite a huge challenge, because most of this analysis up until now has been done manually by individuals. So it's a very time-consuming and a very costly process developing these reservoir models, which will tell us how fluid flows in the subsurface and how we can actually optimize gas or oil extraction or carbon dioxide injection into the subsurface. Dan, can you go to the next slide, please? Thank you. Oh, no, one forward. Right, so one of the tasks in this theme is something you're going to be hearing more about from Brian, and really looking at how we can use machine learning to improve the algorithms and improve data analysis for a variety of geophysical applications. And you'll be hearing more about that from Brian, so I won't be talking, won't be reviewing that anymore. Brian, Dan, can you move on to the next one? So the second theme that we focused on was looking at safer production in offshore reservoirs. As Dan alluded to earlier, when things go wrong in offshore production, they can go very, very badly wrong. And so mitigating the risks to production really represent a really important objective, both for producers and people living in the area, in the regions that production is occurring in. So obviously one of the main objectives for this theme is to develop tools that will reduce the risks of catastrophic failure during production. But as well as reducing the risk of catastrophic failure, we also want to develop tools that will mitigate the environmental impact when there is a problem. So Dan, can you move to the next slide, please? So, for example, one of the main tasks, one of the main problems that we have when there is a failure is understanding where pollution, where oil is going to end up in the offshore regions. So, in order to do that, we need accurate information concerning currents that will transport the oil to various different places. And in fact, this is one of the aims of one of our tasks. Dan, could you move to the next slide? In task 8, a group from Hebrew University in Tel Aviv has developed very, very high resolution maps that can tell us how the currents are moving in the offshore region in the Israeli continental shelf. And what you can see here is some of the results that they've already got, where they've implemented, both measured the currents using radar technology, and they've developed a way of predicting how oil or surface contaminants are going to be transported throughout the region. And what you can see here on the left, for example, is the green square represents an oil spill somewhere off Egypt, and you can see in the right hand image how it's been transported about a month later, all the way around the Eastern Mediterranean Bay. Now, and you can imagine that that this kind of information, these kinds of tools, are crucial if I'm going to try to mitigate the impact and I want to, of these kinds of spills, and if I want to deploy my resources in a most effective way to reduce the environmental impact of these kinds of spills. Next slide, please. The third theme that I'm going to talk about is the risk assessment for seafloor infrastructure. Now, we often think of problems occurring on the surface, but much of the seafloor infrastructure, such as pipelines, are vulnerable to all kinds of geological processes. We think of the seafloor as being a very static environment, but in fact, it's very dynamic. We can have we can have movements of rock, we can have earthquakes, and various things occurring in the subsea floor that can pose a threat to pipelines. And so, in fact, one of the topics that we've been looking at, Dan, could you move to the next slide, is looking at how the injection of carbon dioxide or any other fluids into seafloor can actually induce seismicity. And this is a major problem, not just for seafloor installations, but also in continental for injection of fluids into onshore installations. And so, Dan, could you move to the next slide, please? So one of our projects has been looking at this particular issue and developing models that can predict when we're going to actually have an earthquake. So what you can see here is one of the models that has been developed by Hebrew University in Tulane, and along the x-axis here you can see this blue line, and that's the increase in pore pressure in the model, and at some point the pore pressure it reaches a critical point, and there's a jump in the porosity. And what that model is predicting is the onset of seismic activity. So what they've actually done is they've produced a model that can predict when a rock will fracture and produce seismic activity and an earthquake. And you can imagine that this model is going to be really crucial for designing workflows when you're injecting carbon dioxide into the sea floor, or actually any other scenario where you're injecting fluids into the subsurface. And I think at that point now, I'll hand it over to Dan again.
All right, thank you, Simon. I'll talk briefly about theme 4, which in a traditional view of the world represents the downstream portion of the consortium. And that what we are looking at doing is identifying better ways to utilize carbon to make molecules of interest, which could include fuels and chemicals. And certainly one thing that is a topic right now is the idea of valorization of carbon dioxide. And to that end, I just want to show something briefly. This is a nice collaborative team between the Technion Institute, Louisiana State University, and Tulane University, where the team is looking at reacting methane with carbon dioxide to make something called synthesis gas. And this is a product stream that can be used to make things like methanol and precursors to plastic. And what we have shown here, which actually ties nice to the prior center's discussion, is this is a high temperature reaction. It's very demanding, and to make materials that will catalyze this reaction for long periods of time. And what the team found is that when they take a nickel doped cerium oxide, and do atomic layer deposition and put a thin shell of aluminum on it, the take-home message of these plots is that we can make catalysts that are much more stable and durable to achieve this chemistry. And this is kind of a grand challenge problem in this space. So this is an exciting example of advanced materials letting us do something with carbon dioxide we can't really do well right now. And then the second brief example I'm going to give, which is a Louisiana-centric project at the moment, but is in the process of expanding to colleagues in Israel, is the direct conversion of methane to methanol. And we'd want to do this for two reasons. One is that the current approach to making methanol from methane is a very energy-intensive, high CO2 emissions process, and is also very expensive. So if we could directly convert the methane to methanol, this would have economic advantages, but it would also clearly have environmental impacts that would be positive in mitigation because of the dramatic reduction in energy input to produce the methanol. And what we have shown here is there's a bar in green on the far left of the plot. That is a zeolitic catalyst material we've developed for this direct conversion reaction. And if you look at the red dot inside the blue bar there that's highlighted, it's 2.5 times larger than the state-of-the-art material. So we appear to be making positive headway on a direct conversion technology to make methanol, which is currently used at on the order of 80 million metric tons a year. So we're pleased with how the center is doing. We're making progress on a range of fronts. And my technical gaffes with the PowerPoint aside, we hope you found this enjoyable. And at this point, I'm going to stop sharing my screen and let Professor Summit take over and show you some of the wonderful highlights from his work with Haifa.
Okay, thank you, Dan and Simon. Can everyone see my screen at this point?
Now,
no,
we see. Go ahead.
Okay, all right. So I want to talk a little bit about the work that we've been doing as part of this consortium. And specifically, I want to talk a bit about our work on using machine learning for a geophysical application. This is a collaboration between the University of Haifa and Tulane University. So the topic of this is dealing with synthetic aperture sonar scans of the seafloor. So just at a high level, what this is it's a scan of the seafloor that results in an image that gives sort of the height and the terrain of this image. It's usually taken with a underwater vehicle, either autonomous or remotely driven. So what we want to do is we want to use these scans. They're very high resolution at a centimeter scale, and use these scans and in a way classify any sort of features in the ocean surface, the ocean floor surface, in the hopes that we can detect any anomalies that would lead to a, say, landslide, and especially in the areas around, say, a pipeline that would be significant to detect these in advance. So this is our collaborative team. It's sort of the ideal collaborative team to try to answer this problem. So we have Itzhak Mitkovsky at University of Haifa. He is a geoscience expert, and in particular in marine exploration. So he knows how to make these SIS images and is currently at sea, if I'm not wrong, sort of acquiring more data. And then locally here, we have Cynthia Ebinger, who is also a geoscience expert, but deals mostly, well, she deals, part of her work is in computational geoscience, which leads directly into me. I'm an assistant professor in the Department of Computer Science here, and my research is in image processing and large data processing. So just a little bit about the acquisition. So ITSEC has this remote operated underwater vehicle that has this sonar attached. He does scans of the Eastern Mediterranean. And this vehicle also has a high definition video attached to the vehicle as they drive it around on the seafloor and make scans. So we have this really rich data set of this terrain with an attached video streams in high definition of what they were seeing while they were doing the scans. This is all sort of geotagged and makes this sort of very nice data set. Over my shoulder through this, I'm playing one of ITSEC's videos, so you can kind of see sort of what the data set is. All right, so what we want to do is we want to build a supervised machine learning approach to classify different areas, which means that we need an expert annotation of images to drive a machine learning model. So the first sort of hurdle that we had to overcome was that these images are very large. ITSEC had problems even loading these images. They could be on the order of megapixel to gigapixel, which is billions of pixels. So we needed to build a viewer to allow someone to view this quickly and annotate it quickly. So this is our first viewer to do this. And this was used by Cindy's group, in particular, Hayden Holcomb, one of the students working with her, to annotate the data sets. So we have a preliminary annotation from this. So Hayden had to, watch the video and load the viewer and in a way mentally make the matches in order to be able to do this annotation. So as the next phase, what we actually built was a full annotation system. And this is what Hayden is using right now to refine his annotations. So this new system plots the position over here on the left of the underwater vehicle as it goes, the geotag position, overlaid on top of the SAS scans. And also it has the videos, any video streams associated with this acquisition session. So everything is synced such that if you move the video, you'll see the position moved, this blue dot here. If you click on a path, it will scrub the video to that exact location. So this will allow fast annotation in the future and more accurate annotation. So this is going to be the basis of the system we're going to build to classify these underwater features. Okay. So now that we have the annotation, most of the work has been focused on how do we build a machine learning approach to be able to classify the data. So our group has an expertise in topological data analysis, and in particular, we're using persistent homology, which is a branch of topological data analysis. So at a high level, what this is it treats an image as a terrain. As you can imagine, this is ideal for our situation where this is a terrain that we're dealing with. And what it does is it flood fills from the bottom of the basins all the way to the peaks of this terrain by function value. So it sort of fills in the basins like you were filling in water into this terrain.
Brian, 1 minute.
Yeah,
1 minute.
1 minute. Sorry. Okay, quick. So we use this approach, okay, this connectedness, and it builds this persistence diagrams, okay, and these are the basis for our machine learning approach. As you can see, just from a high level, they look fairly distinct, so it was a sort of a good basis to use. All right, so we're using what we call a deep learning metric model, where we input the images, we input the persistence diagram, we let the machine learning approach learn a feature vector that is the class that gives good separation in this classification. And right now, our preliminary classification using this deep learning approach is getting about 88% accuracy. We'll sort of refine this with further annotations and more data as ITSEC makes it. All right, so that's it. Thank you very much for your time. I'm very excited to present this work. And thanks.
Great. Thanks very much, Professor Shantz, Professor Emanuel. Thanks very much, Professor Sama, for the great example of US-Israeli collaboration with the University of Haifa and their system. Thank you very much. So now we're ready for the Energy Cyber Consortium. I invite Professor Yang Wang from Arizona State University and Dr. Rami Puzis from Ben Gurion University of the Negev the consortium leaders. Please, gentlemen, the stage is yours.
Hello. So together with my colleague, Professor Yang Wang from Arizona State University, we are going to present you the cybersecurity R&D initiative in the energy domain. It's a new consortium that is targeted to develop resilient, robust monitoring and filtering capabilities to protect the energy systems from cyber attacks. Please click. It is not surprising that critical infrastructures are constantly under cyber attacks by major state actors as a part of the global cyber warfare. Last week, we have witnessed an exposure of a large campaign against the Indian power grid, supposedly executed by Chinese hackers. So in order to tackle these attacks, next slide, there is a need for a resilient and robust monitoring and control capabilities, combining cybersecurity and the energy infrastructure knowledge with advanced machine learning. We are rolling up our sleeves to collect data from 2 layers of the industrial control systems: the information technology layer, like servers and computers, and the operation technology layer, such as controllers, sensors, actuators, and so on. In order to do this, please click. We have collected leading members from industry and academia united together to form the ICRD consortium, capable of solving the security challenges associated with cybersecurity of critical energy infrastructures. In this consortium, we have service providers, we have technology providers, utilities, academia, and the great minds of cybersecurity and machine learning united together to solve the tough cybersecurity challenges. Next. We believe that the success of ICRD relies on 3 pillars. The engineering and the OT experts are working hard to build the cyber physical laboratories and simulators to produce data from heterogeneous devices under various attacks, to provide it to the R&D activities inside the project. Experts in artificial intelligence in the industry and in the academy are working to produce machine learning and anomaly detection algorithms that are capable to pinpoint the tiniest clues of adversarial activities in the huge amount of data collected. The cybersecurity experts guide the development of the machine learning against the AI used by the attackers. Because when the attackers know what kind of detection algorithms and detection capabilities the defenders are developing, it is very easy for them to avoid detection and remain under the radar. So adversarial AI against AI is one of the huge challenges of this project. Please, next. Alongside the adversarial AI, data collection is also an issue. For example, we need to protect the privacy and security of the consortium members that are providing the data. And we need to develop monitors that cannot be manipulated by the attackers, a trusted monitor that yet produces accurate results. Next. This consortium is only 6 months old, but we have already achieved some progress in this project. For example, 2 cyber labs are being built right now, containing devices and technologies from multiple partners. Derek US combined with Otorio, Meptagon with RAD, SIGA, Otorio, SCL, and ASU University. Data sharing and dissemination is already taking place with 2 data sets already being sent, disseminated to partners. And they are already working on anomaly detection algorithms. At least 3 academic papers are being currently under review. And we hope that these technologies will be productized by the industrial members in the next 2.5 years. Yang will now present a few showcases of the collaboration between our partners.
All right, thank you, Rami. This is Yang from ASU. So as you can see, we have 3 themes. And so far, we are focusing on the project number 1. Here, project number 2, we have some progresses. So to show you what we are doing for CPS data preparation, I'm going to show you our demo. So first, we let the speakers from the consortium to talk. You can see that we have monthly webinars from consortium members. This is Nexon from United States. This is OPARTY, also from United States. And we have upcoming talks from Israeli side. So people talk to each other and understand the need. Second, we are consortium that is data extensively focused. So you can see we already have a lot of data that is huge. And here I want to show you some geographic information. For example, this is United States, and this is West Pennsylvania, Pittsburgh neighborhood. And you can see that we already get the data from the local urban area. This is from the smart meter that is at the residential level. So we can reconstruct the energy infrastructure even if there is a cyber attack. But anyway, so this is like the foundation. We want to make sure the consortium members know what we are working on, what the energy infrastructure looks like. Second, we also look into the temporal information in addition to the spatial information you saw just now in Pennsylvania and in Arizona and also Israel. So this is a time series data that is from energy storage devices. This is the daily pattern. And what we have is we have different data logs, who is doing what at what time. And you can see that the energy are flowing right now from the battery all the way to the power grid. So in summary, we are doing data collection in different domains. And third, you may ask, what are we going to do exactly? So this is a work that we have done in the past. So basically, we will build up some platform like what you are seeing right now. On the left-hand side, we have some clicks for cyber protection and for monitoring and for control. And then with different functions, we are going to look into the energy infrastructure in different color, in different domain, have different cyber protocols that is enforced at different places. And then we can do different kind of visualization analysis on the right-hand side to see what is happening. And we can also click on the figure to have interactive map for the system operator to see. For example, we can use it for energy grid, like a gas system, power system. We can also extend it to water system if you want. And now I'm going to do the final demo. That is our grid in Phoenix, Arizona. So as you can see, we have a supercomputer that can zoom in millions of points simultaneously based on the data that we collected. And we can do data analytics at different level. For example, right now, I'm trying to show you how I try to look into one region. For example, I'm very curious about what is happening over there. So then the data will focus only over here and do different kinds of analysis simultaneously. So for example, over here, I can try to choose a region, and then you can see the data and the visualization at other places are interactively changing all the time. So we have different kind of tools for our consortium members to use and to develop the cutting edge technology. So now I'm going to conclude my presentation with Rami to show how powerful we are. So here, this is a list of the major consortium members who are doing research. So there are 60 members at least, that is on the forefront. So Arizona State, BGU and Georgia Tech, 3 leading universities, and about 10 consortium industrial members who are actively working with us. I don't know, like a meeting per day to discuss what we can do. And then we also have very strong interaction between United States and Israel. For example, we have meetings between MITRE and also Maptagon, and we have meetings of SEL and also BGU. Probably we have 20 different small subgroups and working force that are working on individual parts. So finally, I want to show you, if you don't know Arizona State, so this is our team. And this is, the school is focusing very much on the investment into this consortium. This is our engineering team. And this is Ethan. It's a pleasure to host the talk. This is our school director and many faculty members. And this is a demo that we did. We not only have the software, we also have the hardware. Finally, I want to call for participations. So if there are any audience who are the utilities, security service provider, integrator, and researchers, please feel free to connect us. We are very happy to work on joint projects to make commercialization happen as soon as possible. So this is the end. Thank you very much for your time.
Thank you. Thank you very much, Professor Wang and Professor Dr. Pouzis. You are our youngest consortium, but we see already significant progress, and we wish you a lot of success in the future. Thank you very much.
Thank you.
Okay.
So for our last consortium, the Energy Water Consortium, I invite Professor Aaron Pachman from Northwestern University, the U.S. consortium leader. Will join him Professor Menachem Elimelech from Yale University and Professor Jack Gilron from Ben-Gurion University to present one of the ongoing projects. Gentlemen, the stage is yours.
Thank you, Eitan. And Jack, please start the slide deck. I'm Aaron Pachman. I'm a professor of civil and environmental engineering at Northwestern University and the U.S. director of CoWork, which is the Collaborative Water Energy Research Center. CoWork is a consortium of 12 institutions, including major universities, companies, water and wastewater utilities, and Argonne National Laboratory. Our activity is fully binational.
Can you move to full screen? Full screen.
Jack, return please to your presentation.
And okay,
do the swap. Yes, do the swap and click hide below. Hide.
Okay.
And go to the next slide, please, Jack.
Okay. There.
CoWork's mission is really to leverage the full capability of the U.S. and Israel with a focus to reduce the energy intensity of cost across the entire water spectrum. And the way that we aim to achieve this is by developing new materials and technologies, taking them out of the laboratory, scaling them up, and pilot testing them at scale in collaboration with our industrial and utility partners. We have 3 main areas of focus: desalination, wastewater use, and resource recovery. And we use a systems approach to this, meaning that we aim to understand the benefits of new technology and new materials in terms of energy intensity and cost at the whole system scale. Next slide, please. Our activity is organized into 6 projects. The first one is on desalination, and you'll hear some of the results of this from Jack and Many shortly. The second one is on selective and anti-fouling materials, led by Jeff Elam at Argonne National Laboratory, and using the capability of the Manufacturing Engineering Research Facility at Argonne in particular. The third project is on nutrient and energy recovery from wastewater, led by Amit Gross from Ben-Gurion University, and involving a large number of partners, including both Mekarot and the Metropolitan Water Reclamation District of Greater Chicago. The fourth project is on trace organic pollutant removal, and this has shifted, driven by essentially market forces, towards PFAS removal. It is co-led by Will Dichtel from Northwestern and Rosa Gwynn from AECOM, So this features a very tight partnership between university, industry, and also the wastewater utilities. Fifth technical project is on low energy water reuse, which primarily features wastewater reuse using injection or infiltration of treated wastewater into the subsurface. And that is led by Alex Furman from the Technion. And finally, our energy water systems analysis project is evaluating all of the other ones. So we have objective consideration of energy and cost aspects of all the water technologies. And that is led by Jennifer Dunn from Northwestern with collaboration, partnership with all of the other projects and team members. Next slide. I'm just going to highlight a few of our key accomplishments. I really wanted to emphasize that every one of those projects is fully binational. All project teams, all activities involve both Israeli and US researchers, industrial collaborators, and national lab personnel. We have been very successful in starting in pilots. Within the first year, we had achieved pilots at some of the largest treatment facilities, both in the US and Israel. And that includes a set of technologies, as well as the soil aquifer treatment system, which you can see pictured on the right. I'd also highlight that we have already achieved 3 new intellectual property advances, one for a new material for trace organic sorption, the second for a new manufacturing process to improve selectivity of membranes, and the third, a new set of desalination processes that Jack will describe. And with that, I will turn it over to Jack to discuss the project activity.
Thank you, Aaron. So before I go into the high recovery desalination, I want to explain why. If we think about the challenges that both Israel and the US are facing, there are limited water resources, so we need to reutilize every drop. For example, now in the Western US, you're dealing with a mega drought, which is the worst in 1,200 years. The highly saline brines that are left behind can also be an environmental headache, and the cost of evaporating them to dryness is either high or very land intensive. Typical removal costs are $2 to $3 a cubic meter of brine, whereas the product itself only costs about 40 to 50 cents a cubic meter. Energy costs for thermal evaporation are on the order of 25 to 30 kilowatt hours a cubic meter. So if we can find a way to reduce brine volume and reduce energy inputs to reduce that volume, that will be a big advantage. So in order to go to high recovery desalination, there are certain technical barriers. First of all, there are sparingly soluble salts that can coat the membranes and reduce production, things like silica, gypsum, calcium carbonate. And as the recovery increases, you pull more water out of your feed water, then the small volume that's left behind with the retained salts, the concentration of those rejected solutes are going to increase, then the supersaturation increases, and that can coat and plug the membrane. So the other technological challenge is that highly concentrated solutions that require extremely high pressures to treat, much higher pressures than by conventional reverse osmosis, and this is a challenge for pumps and other equipment. The alternative to thermal desalination, which is energetically less favorable, can be seen in the fact that thermal requires, as I said, 25 to 30 kilowatt hours per cubic meter of brine, whereas if we can find the right way to combine these various membrane streams, we can reduce this to about 7 to 8 kilowatt hours per cubic meter of brine. So with that, I want to show you an overall flow sheet concept of what we're doing. You can see it here. You can start here with the feed. The feed's coming in at 0.3%. It gets pre-treated to remove the hardness so that it won't scale the membrane. You have reverse osmosis. The rejected brine from the reverse osmosis is now fed to electrodialysis. This is a special electrodialysis, as I'll describe in the next slide, that retains the hardness in this, what's called the dilute stream, which becomes product, and the silica. So the silica and the hardness are passed on to the product, and that's an advantage. And then the other ions, which is mainly sodium chloride, is low in hardness in silica, and that can go into this low salt rejection RO, which Professor Elimelech will discuss in the second half of this talk. But you can see that different universities and institutions from both the US and Israel are contributing to this process. With the Technion on the pretreatment, we're working on the monovalent selective electrodialysis, and Yale is doing the LSRO. So now I'll just give a little bit more description of what's going on with this electrodialysis step. But before I do, I just want to show you that if we do this right, we can get a highly concentrated brine at the end. We start with 0.3% of the brackish water, and the brine we're left with at the end only has 13 to 23%. This is less than 1% of the original volume. So as I said, here at BGU, we're working on what's called monovalent selective electrodialysis. What that does is, using an electric field, it pulls out the sodium chloride, which you don't want to have in your product water, and transfers it over to a concentrate stream. And it leaves what are called the hardness ions and the silica in the product stream. Now that's an advantage for two reasons. One is that the hardness actually is a desirable property in the product water, whether it's for potable water or if it is for agriculture. It actually contributes in both cases. And by keeping the silica in the product water, you prevent the silica, which is a sparingly soluble salt, from scaling up this last process here. So that shows you how we're doing this, and you can see that in terms of the volumes involved, if we start with the initial volume here of QF, by the time we get done with the electrodialysis, that can be down to only 2% of the original volume that we put into the system. So with that, I'll now turn over to the next step. I'm going to skip this, and that is the pretreatment, which involves either a cation exchange column or what's called capacitive deionization, and Meni will discuss this next.
Okay, thank you, Jack. So I will start with a description of the first process. Next slide, Jack. Okay, so the first one, alternative to reduce the concentration of divalent cations that cause all these scaling, is the cation exchange resins. And this is a quite conventional technologies that is used for selectively removing some ions. And you see on the left side of the diagram, you see some stream with high concentration of calcium and magnesium. When it goes up to the top, it's lower concentration. And the challenge in this technology is really to find a regeneration solution which is not expensive and sustainable. And this is really the hurdle of this technology. So if you can find such solution, it will be great. And let's go to the next slide. So this is an example, and again, this is work done in the laboratory of Ori Lav at the Technion, and they are tested these cation exchange resins to increase the water recovery of two desalination plants in Israel, one of them in Elat, in the southern part, and one of them in Ma'agan Michael, the one that we will be using. And indeed, by using this cation exchange membrane, they were able to increase the recovery, as you see here, quite significantly. And the innovation here that they were using seawater as the regeneration solution. Of course, the desalination plant should be relatively close to the sea and the ocean. And in a way, this is what we were doing also in our technologies I'm going to show you later. So next slide, please. So the second technology, again, to remove divalent cations is a capacitive deionization or electrosorption. And this is the work done by Matthew Sass from the Technion in Israel. And in this technology, again, it's an electrochemical technology, more like a battery storage. You have a carbon electrode and you store ions in the carbon electrodes. So the idea here that you store the ion in the micropores of the carbon electrodes, and you want to make it selective so you can store the divalent cations and not the sodium. So Matthew Sass was found a clever way to functionalize these micropores by sulfonated group. And he was able to show that you can really have all the micropores full with divalent cations and almost practically zero sodium. So this is what you see here in the middle of the diagram. It approaches a selectivity of, in principle, infinity, which is really quite innovative and a breakthrough in the electrosorption technology. Next slide. So now let's go to our process and talk about, again, the low salt rejection RO. And here, we're using the capacitive deionization or the cation exchange resins, and we will be using the brine that you come from the low salt rejection RO as the regeneration solution for the cation exchange resins. Next slide. And this is what you can see here. The brine, again, once we concentrate it, part of it can go and be used to for the cation exchange resins, making the process quite viable economically. So next slide. So I would like to talk about the low salt rejection reverse osmosis. Again, a technology that we developed here at Yale. And again, there are two publications based on CoWork that you see here on the bottom, right. And this technology is in principle, it's a membrane base, which already tell you it should be more efficient than thermal. Next slide. Okay, so the first stage you see here will be the conventional reverse osmosis that you have just a complete rejection of salt. And the innovation here that the other stages, second, third, or if you need it fourth, will be low salt rejection. And if you just do the right configuration with the right recycling, you can achieve a process with very, very high water recovery. So again, here the product water will come from the first stage, and the brine will come from the last stage. Next slide. So we have done a very detailed, full-scale modeling and optimization. Again, you need to optimize the salt rejection of each of the stages beyond the first one. And here I'm going to show you some results based on our process modeling of the brine concentration that you can achieve in the left column, the blue bars, or the energy consumption, the red bars. So if you take two-stage RO, you see that we can concentrate water all the way to equivalent of 2 molar, which roughly almost 4 times more than the salinity of seawater. And if you go to 3 stages, you can do it to 2.6 molar. And you see the energy consumption by the red bar on the right-hand column, they're quite low. You're talking about 3 or 5 kilowatt hour per cubic meter. And to remind you what Jack mentioned earlier, the thermal technologies are about 25 and even 30 kilowatt hour per cubic meter. Next slide. So we also collaborate with researchers within CoWork and also some other big centers. And I will show you some example. For example, we collaborate with the laboratory of Jennifer Dunn at Northwestern on a detailed techno-economical analysis of the low salt rejection reverse osmosis. The idea is really to see what will be the cost. And also we will do some analysis to find some innovations to further bring the cost even lower. Another project with the National Alliance for Water Innovation, this is the DOE Water Hub, $100 million investment for the coming 10 years. And we collaborate with the laboratory of Tzachi Kath from Colorado School of Mines. And we will be building a small pilot just to test our basic modeling, again, pilot for the low salt rejection RO, and calibrate the model if needed. And this will provide valuable information when we go to the big pilot for the scheme that Jack showed you initially. So thank you.
Okay. Thank you very much, Professor Pachman, Professor Elimelech, and Professor Gilron. It's great to learn that you already have working pilots and the great collaboration between the US and the Israeli teams and the progress that you just showed us. And we wish you continued success in the Energy Water Nexus Consortium. Thank you very much for your participation.
Thank you, Eitan.
Thank you.
So we are almost at the end. Thanks to all the speakers and the presenters. Allow me to use this opportunity to thank the dedicated staff which supports the management and operation of the US-Israel Energy Center, Ms. Natalie Galperin, CFO, Bird Foundation, Ms. Tal Fishelovich, Director of Partnerships, Energy Center, Ms. Chava Duchan, Office Manager, Bird Foundation, Ms. Shiri Freund-Koren, U.S. Coordinator, Energy Center, Ms. Orion Tabib, Finance Manager, Bird Foundation, Ms. Maa Wakile, IT Manager, Bird Foundation, Dr. Tzvi Tamari, Coordinator, Energy Storage Consortium, Dr. Ori Dor, Coordinator, Fossil Energy Consortium, Mr. Einan Lichterman, Coordinator, Energy Cyber Consortium, and Mr. Uri Atir, Coordinator, Energy Water Nexus Consortium. So this concludes the presentation of the 4 consortia of the U.S.-Israeli Energy Center, which, as you saw, I hope you were able to enjoy the significant collaborative innovation, joint innovation that is being done by all the researchers, the companies, and the research institutions. So thanks very much for attending. And with this, we conclude the webinar. Thank you. Goodbye.